Good morning. So we are going to start our next to last unit. And again, this is just going to be a second mini unit. It'll go pretty quickly. We'll do it really over the course of the next 2 weeks. And some of you are going to have some background information on this because if you're in physics, you know the idea behind vectors, you know how they work. So some of this is going to be really quick and easy for you. This first little lesson here is just a basic understanding of what a vector is. So I want you to take a minute and go ahead and hit pause and read the first two slides. This slide and this slide, please. Just go ahead and hit pause and read that to yourself. Okay, so one of the first things that you should have read is this idea that there are different quantities that we often reference in mathematics that have various representations, specifically physical quantities such as temperature, length, area. They can be measured just by a single number. You spend a lot of time in algebra and geometry in particular, finding the value of a temperature, the value of a length, and you put a label on it like feet or even feet squared or a volume that has a cubic square inches, and either way, those physical quantities are given as a single numerical answer. But other quantities, such as force, velocity, acceleration, all of those require both two things, both a size and a direction. We're going to reference it as a magnitude and a direction. So to reference quantities that need two different representations, we're going to use a vector. Now, you would have already read this, hopefully, if you hit pause, but a vector is a way to represent the direction of an object as well as the size of that movement. So we reference vectors using typically a variable, lowercase with an arrow over top, typically. And we can sometimes, if needed, we can represent the vector as a bold script, which we're going to sometimes see in our own textbook. And other times when it's just through handwriting, we just put the arrow over it to reference it. So I've drawn here what we're going to reference as this y vector, and we can just label it just by putting the variable and the arrow on top. And sometimes we're going to need to reference parts of the vector. To do that, we're going to label two ends. We're going to label its starting point as its initial head. So we're going to say, hey, this is my initial point of the vector. We can also reference it as the head of the vector. And wherever it stops is correspondingly its tail. We're going to also, this should sound like angles, we're going to also reference this as the terminal side of the vector. And with any given vector, it has both horizontal distance, positive or negative, as well as vertical distance, also positive or negative. And it's always from the tail to the head. So we describe the movement here according to what we are going to refer to as components. The components will describe a horizontal distance and a vertical distance. Now that may not make a lot of sense yet, so go ahead to the next slide, and we're going to go ahead and start to look at a specific vector in a specific location. So we're going to draw a vector that starts at the ordered pair 1, 1, and this is going to be its initial starting point, or initial head, and it's going to stop at 3, 6. Its tail will end at 3, 6. So when we reference this vector, we're going to reference it according to a horizontal distance and a vertical distance. A horizontal distance, a vertical distance. So we ask ourselves, hey, how do you get from 1, 1 to 3, 6? Well, to get from 1 to 3, we move 2 to the right. And to get from 1 to 6, we move 5 up. The components of this vector are the components 2, 5. 2, 5. Now, you might be wondering, well, does that mean then that there are other vectors that have the same components? Yes. Equivalent vectors are vectors that have the same length and are pointing in the same direction. Code for, they have the same components. Notice this, their positions do not matter. So it doesn't matter where P, Q, R, and S are located. Take PQ, for instance. PQ starts at 2, negative 1, and Q is at 5, 3. So from P to Q, we're at 2, negative 1, and 5, 3. So if I find the components on that vector, then I'm going to compare it to RS, negative 4, 1, and negative 1, 5. I want to know, are these equivalent? Do they have the same length, and are they pointing in the same direction? Their positions do not matter. Then we need to determine what are the components of PQ, and what are the components of RS. Go ahead and hit pause for a minute, and just based on our previous slide, go ahead and find those components. What you should notice is that the components here are over 3, up 4, equivalently from R to S, over 3, up 4. Because these have the same components, these are considered equivalent vectors. Now, in the meantime, what you should also be noticing is that I actually am finding, essentially, a formula for the components. My request, quickly hit pause and just share with somebody how you would explain if you have x1, y1 as an initial point and x2, y2 as a terminal point, how would you find those components? Okay, so we are taking the x value of the tail minus the x value of the head, x2 minus x1 to find that horizontal component. Then we do the exact same thing for the vertical component. Subtract the y's to get a, b. Tail minus head, tail minus head. That gives me my horizontal and vertical components. Now, the cool part to vectors is that I can actually take and begin to perform operations on these vectors. So if I want to, I can take U and add it to V. And in your gut, we'll talk more about this tomorrow, but in your gut, it is exactly as you think it would be. If I want to have a component that was originally 1 to the left and then I go 4 to the right, where will this end up? 3 to the right. If I have a component that was originally a movement of 3 and now a vertical movement of 7, I'm going to have a total of 10. Take a moment and in your gut, see if you can just figure out, hey, how do I perform those operations? Okay, well, if I am tripling U, then what was a horizontal movement of 1 to the left is now a horizontal movement 3 to the left. And what was a vertical movement of 3 is now a vertical movement of 9. It literally just triples. And when I double U and subtract V, this doubling of U gives me negative 2, 6. When I subtract V, and again, we're going to look more at this movement tomorrow. When I subtract V, instead of moving 4 to the right, I'm moving 4 more to the left for a total of 6 to the left. What was 6 up is now going 7 down. So we're going to have negative 6, negative 1, And finally, for those of you in physics, you know that one of the most important aspects of a vector is its magnitude. We have a notation for magnitude. It looks like the idea of an absolute value of v. That is not absolute value in the context of vectors. It is the magnitude. So when I talk about vector v, I want to not only be able to talk about its horizontal and vertical components, but I also want to talk about its size. A way to think about that is to look at vector v here, and we're going to put context on it and say, hey, I've got an initial point at -3, 1, and a terminal point here at 4, -1. And we would say, okay, what are the components of this? Hit pause and quickly list the components. The components, I have a horizontal distance of 7 and a vertical distance of -2. But when I talk about magnitude, I want to talk about size. And so if you consider this a triangle where I have a size of 2 and a size of 7, in your gut, you likely know where this is headed. How would I find the size? I would simply use the Pythagorean theorem. And I could say, hey, -2 squared plus 7 squared is my magnitude squared. So my magnitude is actually the square root of -2 squared plus 7 squared. I'm going to drop down here to finish. So this is actually the square root of 53. The size is square root of 53. So to end today, we're just going to conclude by saying we can take any vector of size AB, and we can recognize that this horizontal component and that vertical component, no matter how or where my vector is located, this horizontal component would be here. My vertical component would be here when this vector is drawn essentially as the hypotenuse of a right triangle. And so how would I find the magnitude of vector v? I would say, hey, that magnitude is the square root of a squared plus b squared. So that is the conclusion for today. We're going to start actually with going over the homework tomorrow and with these application considerations. So you don't have to worry about that at this exact moment. You can enjoy this quick lesson and have a good rest of your day. Your homework is the worksheet that's on the shelf. That whole thing needs to be done for tomorrow. It'll be a quick 1-point check. Just hold it up when you come into class tomorrow, so make sure you have that done. Hope you have a good rest of your Monday.